Hi. In this video, let's take a look at a static field meter. I will take it apart shortly and we will see what's inside. But before I do that, let me briefly explain what a static field meter is and how it works. An electrostatic field meter, as its name implies, is a device used for non-contact measurement of electrostatic field of an object in volts. It is an instrument most people probably have not used before. And due to it being such a specialty device, it is very expensive, even buying a used one. But it is quite useful in a lot of situations. For instance, for the safe handling of ESD sensitive devices, we need to know whether the environment is harmful to them. When the static electric field is too strong, any accidental discharges through the devices can compromise the integrity of these devices and even possibly destroy them. Devices with metal oxide layers, such as MOSFETs and CMOS chips, are particularly sensitive to ESD. Each device's ESD ratings, depending on the model used, for example, human body model HBM, charge device model CDM, they are usually specified in the datasheet, and with the human body model figure typically higher than the charge device model rating. A typical damaging voltage level for ESD is only several hundred volts, which can be easily exceeded if the device is not properly packaged or handled. So to get an idea of what kind of static voltage we can expect from some charged objects, let's take a quick look at a few experiments. Here is a Plastic Systems 42721 static field meter. The company is now called, I believe, ESD Systems. This particular meter was made back in 1996, which is roughly 20 years old. But the operating principle of these meters, as we will see later, is largely the same compared to the more modern ones. So now let me turn this on and we'll measure a couple of objects. So basically all the meters are kind of similar in operating principle. Here I just press this button and it turned on. And now this kind of meters usually needs to be calibrated by pointing to a ground level object, meaning ground in terms of the voltage reference. So here, as you can see, when I point it far, it's approximately already zero. But just to zero it again, I will just hold the button till it reaches zero, and then I release it. So that's a calibration procedure. So now if you look at it carefully here, on top of the unit, we have a sensor right here. And these two lights are blinking, and they are actually arranged such in an angle such that when you have the correct distance from the light and your surface, so this is approximately 1 inch, then these two spots are going to be overlapping each other. So the idea here is when you are trying to measure, you try to hold it at a distance where you don't see, a little bit hard to see here, when you don't see these two spots oscillating back and forth, then that's approximately 1 inch. So here is pretty much the distance. And if you go any further, you'll see that the spots started to diverge. And similarly, when we get too close, then the spots start to diverge. So anyway, so that's how we gauge the approximate distance between this and the object we're trying to measure. So the first object we're going to measure is the styrofoam. And as we know, styrofoam is extremely easy to accumulate a high voltage on the surface. So let's see how this one measures. As you can see that we're just getting closer, it's already like 3,000, 4,000, 5,000 volts. So actually that is very high voltage in terms of the so now let's take it back a little bit. It's 1 inch. So right now it's a 1,000 volts, give or take. So this actually is a high enough voltage to damage your sensitive electronics. And so that's why we shouldn't be using styrofoam to package sensitive IC chips or MOSFETs alike. Okay, so that's the styrofoam. And let's take a look at some, another thing is really bad is the plastic bags. So for example, here I have some plastic bags and it's rubbing around, and you'll see that the surface voltage is already 1.5 kilovolts. So that's very high. But the IC packaging material, for example, are designed to dissipate charges. So these kind of red, look seemingly like a styrofoam, actually it's not. So when you look at it, it actually does not register any significant voltage. And so it's only like, give or take 20-30 volts, which is actually right in the margin of error. So of course we also have those anti-static packaging, which everybody is familiar with. But anyway, so that's how in general a Fieldmeter operates. And so any surface that you do your electronic work on, for example, should be pretty. So this one actually, it doesn't really have any charge on it, which is desired. So anyway, so let's take a look at the operating principle of this Fieldmeter, and then we'll take it apart. So generally speaking, there are two different methods to measure electric field like this, and they both employ similar principle. So the first one is, for example, the one that we have here is basically you have a object to be measured that is charged, and we have a sensor here which is enclosed in this grounded Faraday cage. Okay, so here we have a plate, metal plate, and basically whenever you are in the electric field, here we have a electric field E1, and then in turn this metal and the ground, we induce a different electric field, E2. So this E2 is basically a function of how strong this electric field is here, E1, and also depends on the distance, D. So basically, if I know the distance here, then we can calibrate this instrument to basically measure this E1. So that's the general principle of this kind of a meter. Now another one is actually kind of similar. So it's basically almost exactly the same design. In order to get rid of this distance dependency, basically what happened is you have this E1 oscillate around a stationary point or their resting position in a sinusoidal fashion. So basically when this plate vibrates, and you can write out the equation. Basically, when you solve for the E1, it's only going to be dependent on this your charge and has nothing to do with the distance. Now, in reality, it will be somewhat dependent on the distance, but nevertheless, this dependency is significantly reduced as compared to the stationary plate sensor like we have here. So roughly speaking, these are the two different type of measurements. By the way, in some literatures, the second type of sensor, the ones that this plate oscillates in a sinusoidal fashion, sometimes the sensor is called a Kelvin vibrating capacitor sensor. So you can take a deeper look if you're interested in that. But I think our kind is actually, as I mentioned earlier, it's the first kind. This is a fixed one. That's why it has dependencies on the distance between the head and your measuring device and the measuring material. So basically, we have a sensor here, and we have an amplifier. And then we have a display. Now, this is not just an ordinary amplifier because the signal here coming in is very, very small, and it's a DC signal. So we wanted to make sure that we have very little offset so that we can, obtain some meaningful readings back here. So typically, this is done via the use of a chopper stabilized operational amplifier. So now, the principle of a chopper stabilized amplifier is to convert this minute DC signal into an AC signal, and then we amplify as such. So any accumulative errors would be nulled out, because we're only we're only interested in the AC signal rather than the DC component here. Now, let's also, oh, by the way, so also because the sensor has to be ground referenced, typically what happens is they assume that the person is ground referenced. So when we are holding this case, and the case is conductive, and so be it the actual instrument case or the actual sensor case, they're connected, and this should be conductive. So that's how they ensure grounding. Alternatively, you can use this this plug here to plug in a known ground reference. So now for that, which means the case for this instrument has to be conductive. So let's verify that. And now I don't know how conductive this case is. So let's first use a standard multimeter. So let me just change it to ohm range. Let's see if we can obtain any meaningful reading here. Okay, so let's just like that. No, so I'm guessing is that this is actually pretty high resistance. Okay, so for that, let's change it to my electrometer here. So if you haven't seen this one before, I did a video on this very electrometer and discussed when to use it and how to use it. So you can watch that video if you are interested. But now we just set this to a giga ohm range. Okay, so now let's measure the case to see what the reading is. I didn't bother taking that down here, so you have to just follow the camera here. So I'm just going to press this on it, and as we can see, I'm just going to. So this started dropping down to about roughly depends on the pressure I have on the I pressed on against the case. It's roughly like 1 giga ohm, okay, give or take. So basically the case is conductive, and because we're just measuring static electric field, it doesn't necessarily need to be super low conductivity to be able to dissipate the amount of to conduct rather the surface charge from your hand to the ground. So basically, when you are holding this unit, this whole unit becomes at a ground level. Okay, so that's enough theory. Let's take this puppy apart and see what's inside. So for that, let me zoom it out a little bit so we can see the whole thing here. So let me first take out the battery. And I see 2 screws here. Okay, another one. And that's pretty much the only screws I can find. Oh, it does open a little bit. Hang on. That's interesting. Hang on, let me take this off the camera and open it up, and we'll be back. As it turned out, this thing actually doesn't open this way. It actually is quite clever. It slides out this way, and now we can open it up. So here we have our first look inside this field static meter. And from here, we are actually not seeing much. The only thing you can see is this PIC microcontroller, which is what we expected, because this microcontroller is in charge of the displaying, the calibration, and everything else. So there really isn't too much on the back end. But if you take a look here, this is where that metal sensor is, and the metal casing for the sensor is. So here we have the sensor. You see the opening right here, and here's the casing. Now I notice that they actually, this whole thing is actually glued shut to. All right, so glued shut to the board, to the case. In order to open that, we need to get rid of this. All right, this glue. So I think we still want to open it up. Because I'm curious to see what is underneath. So let's do that. So let me do that, and I'll be back. Okay, it's actually easier than I thought. Whatever this thing is to hold that in place, it's actually very easy to get rid of. It may just be some, actually I don't think it's wax, it might just be some plasticky glue type. But later on we can kind of just use wax, I suppose, to put it back if we need to. So now I think we can remove this whole thing, and maybe we still need to remove some of the because the hole has a very tight tolerance here, so we just need to get rid of this glue. I'm not sure why this one is a little wobbly. Maybe it's coming off. It doesn't really matter. Okay, so let's see here. Yeah, so now this whole thing is out. Ah, look at that. So we see what we see here. So here we have a, let me just zoom it in so we can see the parts here. If it can focus. And if not, we can later I'll write it down, so later I can show you. And by the way, I will be posting all the pictures of this onto my blog, so you can always check it there to see the actual part number. Anyway, so here we have a let me just read this. We have a LMC6064. We have a ICL 7621. We also have an LT. I'm not sure what this is. It's either 614 or 10644. So I don't know what that is, but let me take a look, and we will be right back. Okay, so I just looked up the part numbers. The LMC 6064 is a Texas Instruments precision quad op amp, and the ICL 7621 is a Intercells very low input current op amp, and the low input current is very important, as here it's this is the front stage, and it comes right in from this capacitive sensing unit. So any leakage current here are gonna be significant. So this particular IC has a very, very low input offset current. Is only measured at 1 picoamp. So that is definitely chosen for this very purpose. Now, other than that, there's a LT1044. That's just a switching capacitor voltage converter to step up the voltage for some other components here. Actually, on a second thought, this the switching capacitor voltage converter sometimes is used actually to provide the asymmetrical voltage, plus and minus. So we have a plus 9 volts here, and I suspect that this one is actually used to provide the negative power supply used by some of the op amps. So really isn't anything particular here. And I'm actually a little surprised. At first I thought it was going to be a very, very expensive type of front-end amplifier. I suppose that it doesn't really need to be that precise, and a very low drift, 1 picoamp offset op-amp probably would do the trick, rather than a chopper stabilized amplifier. So now, other than that, we really don't see too much in here. And here is a closer look at those two diodes, I mean the two LEDs. They're angled at a certain distance. They're angled in a way that this would focus at roughly 1 inch in front of this sensor plate. And here is an external grounding plug. And let's see what else we can see here. So that's pretty much what there is. So I guess a lot of the magic happens inside this sensor unit, which I'm not going to take it apart because I still want to use this meter. But you know, presumably it's not that different than what I just drew here. So as you can see, you know, the actual electronics part is not that fancy, and probably the cost of the electronics part is, I'm guessing, is, you know, pretty low. But the reason these meters are so expensive is, number one, because of the calibration required to you know, for each production unit, and also they're not massively produced. So, and also I suspect that this particular sensor, capacitive sensor, also is a little bit tricky to make. So, but other than that, you know, it's just a simple microcontroller here, and drive the display and everything else. So now let me put it back. And oh, by the way, so here, if you haven't seen this, this is basically just that the back of our display. So there really isn't too much to this. So I think that's pretty much what there is inside this electrostatic field meter. So now everything is back, and let's see if it still works. No problem at all. Anyway, I hope you have enjoyed the video, and if you learned something new, as always, please give it a big thumbs up, and I will catch up with you next time.